Yeah, now this will be the last part of RSA algorithm lecture, and we will do one simple example. Before that, let me recap what RSA algorithm is all about. We have plain text, or we also call it message block denoted by M, which basically is represented as an integer, any integer between 0 to n minus 1 for some n. But how is value of n decided? We take any two prime numbers pq and multiply them, we get the n. The next important step is to generate two numbers e and d such that if we do this operation, that is we take m to the power e modulo n, what we get will be the ciphertext c, and hence if we take c to the power d modulo n, we should get back m. Okay, that is the main scheme. So m is the plain text, c is ciphertext, and the first equation gives us ciphertext out of plain text by using e, and second equation gives us back plain text after we feed the ciphertext c, and hence e acts like a public key and d acts like a private key in the context of public key cryptography. By feeding back this c is equal to m to the power e, we can write again this as m to the power e whole power d, which is equal to m to the power ed modulo n. In the light of Fermat's theorem and Euler's theorem, if you go back to the video lecture on mathematical preliminaries for RSA algorithm, this relationship is true only when ED are multiplicative inverses of each other, but in modulo n sense. Okay. Now, what does it mean to be to have a multiplicative inverse? We'll see it very soon with one example. But this is the condition on this ED here. We know from Fermat's theorem that E and D are multiplicative inverse of each other if ED modulo phi of n, where phi of n is a torsion function, is equal to 1. We also write it like this: ED is congruent to 1 in modulo n, and hence D is equal to E inverse in modulo n. And I repeat, the choice of D and E should be such that this inverse operation should be very hard, because you are depicting E as a public key, and the condition for public key cryptography is given the public key, it should be very difficult computationally to get the private key. Let's have a digression in between and discuss what do we mean by multiplicative inverse modulo, suppose any number as n. Okay, same will be with phi n. Let's take some example. Let's suppose we have a number 3 and we want to find its multiplicative inverse modulo 5. Let x be that number. So what does it mean? It means 3 times x is congruent to 1 modulo 5. Okay. So what does it mean actually? It means that if you have a number x and you multiply 3 into x and divide it by 5, then the remainder should be equal to 1, right? So that is what modulo definition means. Let's see which number will satisfy it. Now if you take x is equal to suppose 2, right? So you get 5. What is the remainder? Remainder is 0. So 2 is not multiplicative inverse. If you take 3, then 3 times 3 becomes 9. Yeah, before that, I'm sorry, I mean 3 to 2 is 6. 6. Okay. So if you take 6 and you divide this, yeah, so remainder is 1. So it means that 2, when you have x equal to 2, this is indeed multiplicative inverse of 3, right? Because 3 into 2 is 6, and 6 divided by 5, the remainder is 1, which in the language of modulo multiplication means that 3 into 2 is congruent to 1 in modulo 5. Fine. Let's take one more example. Suppose we have a number 5 and we want to find its multiplicative inverse. Suppose x is some number such that it is congruent to 1 in modulo 5. Now what will be this number? Suppose if you take x is equal to 1, then 5 into 1 is 5, remainder is 0. If you take x is equal to 2, then 5 into 2 is 10, remainder is 0. What we find is that this number 5 and the modulo with respect to which we are taking 5, they are same. Even if it is like 10 times x equal to 1 modulo 5, you will find that when the number which we are with which we are dividing the number and the number with which respect to which we are finding the modulo, if they are not relatively prime, then we will not be able to find its multiplicative inverse. For multiplicative inverse, it is very important that these two numbers, suppose if I write like this, a b is congruent to 1 modulo n, then these numbers should be relatively prime with respect to n. That is very important. Okay, so now let's take one more example. Let's say we are finding multiplicative inverse of 3, but this time modulo 7. Now first of all, see, 3 and 7 are relatively prime to each other, so this multiplicative inverse will exist. Let's try it iteratively. So if x is equal to 1, we cannot do it. If x is equal to 2, again we cannot do it, remainder is 0. If x is equal to 3, then it is 9. And let's see what is, so we have to divide by 7, so remainder is 2. Similarly, you try with x is equal to 4, 3 4s are 12, and 7 1s are 7, again the remainder is 5. No. Now take x is equal to 5, 3 5s are 15, and divide this by 7. So 7 2s are 14, remainder is 1. That is what we want. It means 3 into 7 is congruent to 1 in modulo 7, and hence 7 is the modulo, multiplicative inverse of 3 modulo 7. Note one important thing, that the same number 3 has multiplicative inverse 2 when you are in modulo 5, and the same number 3 has multiplicative inverse, I should write here 5, multiplicative inverse 5 when you are doing modulo 7. So this is the way, but as the numbers are very very large, so these 3 and 5 are very small numbers. Take a very large number, 1 9 1 4 7 8 2 6 7. Now try to find it as suppose multiplicative inverse, say modulo 1 0 2 4. It's very huge number. So then you need some algorithm. There is one algorithm for it. It's called Euclid's algorithm, extended algorithm. We will not do that, but there is a way out. But at least it is clear that what multiplicative inverse means. Now let's go back to RSA algorithm and state the other conditions and take one example. Now at this point, first I will recall one more result when we discussed the mathematical preliminary things, that it's not actually mod n. First of all, let me correct it. It is mod phi n. Okay, yeah, so which we have written here, it's my mistake here. Now one more result which I would like to recall here is ed form multiplicative inverse, or we can say E is multiplicative inverse of D if there's a condition that if the GCD of E and phi of n is 1, right? This we have seen there. Basically, if you take any number n and whatever be the number of numbers less than n which are relatively prime, so the quotient of that is phi of n. Okay, suppose if n is a prime number, then phi of n is n minus 1. If n is equal to product of two prime numbers, then you know that phi of n is what? P minus 1 times q minus 1. And if E and D form the multiplicative inverse in modulo phi of n, then GCD between them should be 1. So this is basically the basis of choosing E, because what you do is basically in RSA you generate P. The first prime step is generation of two large prime numbers, then you multiply them, then you choose E such that GCD between E and phi of n is 1. Okay, there's an algorithm for GCD. If you iteratively run it, you can get it. But if n is very large and you do iterative method, of course it will take a very long time. then there are very efficient algorithms to compute GCD. Fine. After you choose E, then you need to do this operation E inverse in modulo phi of n. And this we have demonstrated here, that how to find multiplicative inverse with respect to any modulo operation. Let me first take one example so that it becomes pretty much clear what to do. Let's choose two numbers P and Q to be 17 and 11, and hence n will be equal to P times Q, that is 187. But I warn here that this is just a dummy example. Such small P and Qs are not taken because finding the inverse, multiplicative inverse here is not so complex. Practically very large prime numbers are taken. And let me emphasize here the importance of mathematics again, that to know the prime number, largest prime number after some number, is very important in this case. So hence the number theorists come into here, and they really help in providing us means of choosing prime numbers, large prime numbers. Fine. Now what is the next thing we need to compute is totient function. Everything is modulo phi of n here, and that we did a very small theorem in our prelims video, that a totient function of a number whose factors are two prime numbers here P and Q is equal to totient function of P times totient function of Q. And we know that a totient function of prime number is the number minus 1, so it will be P minus 1 times Q minus 1, which will be 16 times 10, and quotient function is 160. Now in the context of public key cryptography, we now need to generate the public key. What is the public key here? E. So we need to choose E. So what E should be there? Choose such that E and the totient phi of n, that is E and 160, are relatively prime. So there will be many such numbers. For example, if we choose E is equal to 7, again we are choosing deliberately a smaller number so that we are able to demonstrate it here. Otherwise, practically we will take large numbers. Fine. Now the next step is to, in the jargon of public key cryptography, is to generate private key. What is the private key here? It is actually D. So how to determine D? We know the condition for D, that D should be multiplicative inverse of E, that is DE is congruent to 1 modulo phi of n. In this case, it is like D into 7 is congruent to 1 modulo phi of n is what? 160. So the brute force method would be like this. So you go on choosing D starting from 1, 2, 3, so on and so forth. Multiply it with 7, divide it by 160, check the remainder. Or else, based on that, there is a well-known algorithm called Euclid's algorithm. We will not go into that. Anyone interested can see the book. There is a chapter on that. But it is easy to find. It's not a difficult thing for small numbers. But for large numbers, even if you use Euclid's algorithm, finding this D is very, very complex. But for this case, it is not so complex. We can write a Python code for smaller numbers easily. Now, you go and check, and then you'll find that D is equal to 23 is a number such that, you see, 7 into 23, it is what? 161. And once you divide 160 by 161, you get remainder 1. So it means that 7 times 23 is congruent to 1 in modulo 160 way. So that means 23 is multiplicative inverse of 7. So basically you can write actually 23 is 7 inverse under modulo 160. So this inverse operation, which here seems to be simple because we are choosing E small. Imagine E to be very large number. Assume this is E, for example. And finding D is extremely complex, and that is the need. Because E is a public key, D is the private key. Given public key, it should be very difficult to compute private key. Now, in terms of public key cryptography, what is your public key now? So remember that we wrote public key as E comma n. So which becomes 7 comma 187. Similarly, what is private key? It is D comma n, which is now 23 comma 187. Let's take an example. Suppose You wrote something on the computer and then you converted that into binary, and then block of a binary you convert into the integer, and let that integer be equal to suppose 88. Now using the same public key cryptography technique, that's RSA, with the given public key and private key, let's try to see how we can encrypt it. You know that C is equal to m to the power e modulo n, right? So which in this case is actually 88 to the power 7 modulo 187. Now at this point I will not spend time here. I again request you to go back to the mathematical preliminary video. There you will find we have done this in detail, how to do such exponentiations using modulo operations. Based on that, you will get this to be equal to 11. Now if you want to get back m, that is c to the power d modulo n, which is here 11 to the power 23 modulo 187. Again following the same technique, you will see that this will be equal to 88. Okay, so this is because of by virtue of choosing small p small q, hence very small n, small e and small d, we were able to demonstrate this by hand. Now practically you can take very large p, that is what actually is done practically. You take very large 2 prime numbers, then generate n, then you find the totient function of n, then choose e such that e and totient function of n are relatively prime to each other. For that the condition is that GCD, greatest common divisor, should be 1, obviously. Then there is the algorithm for GCD, we can use that. In Python there will be functions for GCD, you can implement that. After finding d, you need to find e, you need to find d, which is multiplicative inverse of e. So you can do that brute forcefully for smaller numbers, but for larger numbers there is an Euler's algorithm, and if you find d, now you can decrypt also, and finding d will be very hard as compared to other operations relatively. So this completes, to some extent, the RSA algorithm with examples, and now we will continue to other couple of topics related to authentication and other security topics. So maybe some few videos will be there which will complete the syllabus of security. Then I will have some supplementary videos to discuss some Python implementations possibly, and also some more concepts which will be just a supplement topics that will be uploaded on the same YouTube channel.